Welcome back to the exhaustive exposition of Module 1. Today we advance to Portion 2, Dissecting Structural Equivalence. Morphological isomorphism, and the rigorous definitions of substructures. Two graphs may look completely different when drawn on a two-dimensional plane, featuring vastly different intersecting lines and edge lengths, yet possess perfectly identical internal connectivity logic. When two graphs are structurally and functionally indistinguishable from a relational standpoint, they are officially deemed isomorphic. Graph isomorphism establishes a rigorous mathematical equivalence between distinct logical models. Let us establish the formal bijective definition. Graph G1 is mathematically isomorphic to graph G2 if and only if there exists a strict bijective function, a mapping that is both one-to-one and onto, between their vertex sets. This bijection must perfectly preserve adjacency. Any two vertices U and V are adjacent in graph 1 if and only if their mapped counterparts are explicitly adjacent in graph 2. To systematically determine if an isomorphic mapping is even possible, analysts rely on evaluating strict graph invariance. An invariant is a quantifiable structural property that must be perfectly conserved during any valid bijective mapping. For two graphs to be considered candidates for isomorphism, they must strictly share the following necessary checklist. Vertex conservation, edge conservation, degree sequence alignment, and cyclic parity. If the degrees of all vertices in both graphs are sorted in descending order, the two resulting integer arrays must match perfectly element by element. Let us test this with a practical analytical inquiry. Proving structural isomorphism. Consider a pentagonal cycle graph C5 drawn as a standard convex pentagon, and another graph drawn as a self-intersecting 5-point star. Both contain exactly 5 vertices and 5 edges. Every single vertex in both graphs has a degree of exactly 2. By mapping the outer perimeter vertices of the pentagon to the alternating points of the star, we perfectly preserve adjacency. Thus, we mathematically prove that the pentagon and the 5-point star are completely isomorphic. They are the exact same graph in disguise. This brings us to a profound structural trap. Inquiry 2. Are two graphs that possess the exact same number of vertices, edges, and perfectly identical degree sequences always guaranteed to be isomorphic? The mathematical answer is an absolute no. While these invariant conditions are strictly necessary, they are incredibly insufficient to prove structural equivalence. Let us examine a devastating counterexample. Cycle mismatches. Consider two distinct graphs, each containing exactly 6 vertices and 9 edges. Furthermore, every single vertex in both graphs possesses a uniform degree of exactly 3. Graph A is a classic bipartite graph known as K33. Because it is bipartite, it mathematically cannot contain any odd-length cycles, meaning there are absolutely no triangles within its topology. Graph B is a triangular prism graph, which fundamentally consists of two interconnected triangles. Despite sharing perfectly identical degree sequences and invariant counts, Graph B contains 3 cycles, while Graph A contains none. The geometric presence of a 3-cycle in Graph B and its total absence in Graph A mathematically destroys any possibility of a bijection, proving definitively that they are not isomorphic. Transitioning to structural fragmentation, we define the concept of a subgraph. Graph analysis frequently necessitates dissecting massive, globally scaled networks into highly localized, manageable subsets. A localized graph H is officially defined as a subgraph of a parent graph G if and only if the vertex set of H is a strict subset of the vertex set of G, and the edge set of H is a strict subset of the edge set of G. Subgraphs are subjected to stringent operational rules. An absolute topological constraint is that an edge cannot exist in a subgraph unless both of its terminating endpoints are also explicitly present in that exact same subgraph. Subgraphs are further categorized based on their relational overlap. Edge disjoint subgraphs are two subgraphs that share absolutely no edges in common. Their edge intersection is the empty set. However, edge disjoint subgraphs may still share common vertices. Vertex disjoint subgraphs are two subgraphs that share absolutely no vertices in common. By the fundamental laws of graph topology, any two subgraphs that are vertex disjoint must inherently and automatically be edge disjoint as well. Finally, we define the induced subgraph. An induced subgraph on a specific, targeted subset of vertices contains all the possible edges from the original parent graph that connect any two vertices present in that targeted subset. This concludes the rigorously mathematical portion 2 of Module 1. You have successfully mastered graph bijections, the deception of invariant sequences, cyclic parity mismatches, and the exact constraints governing subgraph isolation.